Hi guys, I've spent the day yesterday working on the little HHO cell, and again looking at finding the resonance of this cell, and I've drawn a conclusion that I'll give you at the end of this video. But my thanks to Prismatic Zero, because he reminded me that I've got a piece of test equipment that I don't normally use for anything other than my ham radio work, and that's a miniVNA, and this is a vector network analyzer, and this I use this when looking at my antennas, my radio aerials for my ham radio work, and essentially it allows me to find the natural resonant frequency of any antenna that I make. And what I'm looking for with the cell is the natural resonant frequency, so it makes perfect sense to use this tool for that job. But I've forgotten, so thanks for that, I appreciate that. Get a bit focused on doing something one way and you can forget other tools in the toolbox. Anyway, I've made a bunch of little coils here, and you'll hear me saying, or you're seeing my comments to people that these coils are small, or they're delicate, or whatever, and they behave, the cell behaves differently to that I'm normally used to in a tank circuit. And here's a few coils that I've made or designed in the past, and coppersmiths have made coils, but here's some coils that I've worked with in the past, and therefore industrial and scientific applications. Essentially they're made out of water-cooled copper tubes, sometimes rectangular or shaped copper, but it's water-cooled because they carry so much current, typically working into the thousands of amps. Most of my work has been in the hundreds of kilohertz, although some has been in the megahertz range, and that's for industrial and scientific equipment, and with some 3 kilohertz and 10 kilohertz work as well. So these are some of the different coils that I made, and I say just compare those for a moment with some of the coils I'm used to, and point out that the fundamental principle is exactly the same. It's just that where I come from, the powers are higher, but the principle, the theory is still the same. So there's the cell, which you've seen before, and there's that little 2-turn half-inch ID coil that I spoke about. I've just taped up the thermocouple leads out of the way so as I don't break them there. And initially I did my trials using the this 1 metre of coax that I've shown you before, but I found I got all sorts of resonances and harmonics, and oh, that's the miniVNA. So I had that lead connected to the coax lead. I also tried using my normal test leads with the miniVNA, but in the end what I had to do was couple the analyzer directly to the cell. So I got the appropriate connectors there. So now when I connect the VNA there, this goes off to the computer. It's the USB connection there. So now I can't get any closer to the cell other than taking the cell apart than that. But I'll show you the results that I get on the computer. Okay, this is the setup that I shall be demonstrating. I've got the VNA connected to the cell, and the cell is sat on this plastic dish, and that's so that the capacitance of the cell isn't influenced by the table, Okay, I'll show you the computer. Okay, so this is the screen, and I'm going to hit run. Oh, by the way, across the bottom we're measuring frequency, and I shall be measuring from 1 megahertz through to 90 megahertz. I've limited that to 90 megahertz because there's some funny things that happen up at 170 or so megahertz, which I think are just complete spurious signals. So I've blanked those out, and I've got the VNA set on SWR. So this is looking at standing wave ratio, and effectively what that means is it's looking for a point of resonance. And what I'm going to do now is I'm going to hit run up there. Don't know how well this will come out on YouTube, and that's the response that we get there. So, and we can look at the frequency there. We'll look at the minimum SWR, and it's saying that's at 46 megs or thereabouts. Let's just get rid of that. There's probably newer software than I've got here, but that's showing the resonant frequency there, and if we look, we can put a marker there, and that says 47.9 in the middle of that bell, or in the dip of that bell. What I'm going to do is I'm just going to go here, and I'm going to put let's put 3 dB offset on it. Get rid of that loss line. Okay, so that's just lowered that from that top line, so as you can see a little more clearly where the dip is. So that's not a very sharp resonant dip. If it was a high Q circuit, that would be down and up. So, and that's because there's not much capacitance. The more capacitance there is, the narrower that will be, the sharper the dip will be. And that is for the cell when it's dry. What I'll do now is I'll introduce it into the water, and I haven't done this morning. I did it last night. There's no reason why the results should be different, but knowing my luck, anything can happen. I want to get both the water and the screen in shot, so as you can see what happens. Okay, so we'll set it running, and this, what's happening is the analyzer is continually sweeping from 1 megahertz to 90 megahertz, making measurements along the way. And I'll just show you I'm going to tip water everywhere into the laptop, aren't I? And you can see that flashing light, hopefully. That's showing the repetition rate. Hope you're getting that anyway. Right, so I'm going to lower this into the water, and I can't see everything at once again. It's such a shame. Okay, so we're just touching the water, about 1/4 of an inch into the water. And look at that, that's a nice dip, but that's only about 1/4 of an inch of the plate in the water. And you see, that's going down in frequency because the water is adding dielectric, so it's making the capacitance higher, bigger capacitance, lower frequency, the coil staying the same. Okay, that's in. So, give you a close-up of that. Okay, so that's the sort of dip that you get, that little dip there, and let's put a marker on it. So there, and if we look at what it says that marker is, that says the red marker. I'm trying to reach over the tripod and all sorts here. That's saying the red marker there is at 6.5 megahertz. Okay. Just lift the cell out and try not to dribble water everywhere. What'll happen is some of that water will remain in the cell. It will have bridged the nylon washers and in the threads of the bolts, so it's very difficult to get that last bit out. And I'm just going to put that. I've put that cell down on the table now, and this is one of the problems I had yesterday. I had to continually take it apart and dry it to actually see my results. Had the natural condition of the cell been like that, with this lovely dip, then you could very easily go and find the find the natural resonance by any number of means. But as soon as you immerse the cell in the water and you start to get some resistance across it, then of course you dampen the Q. So I reckon that nobody is actually hitting their cell at the natural resonant frequency of the cell. I think that what is happening is that people, including Stan Mears, are hitting the cell with a repetitive frequency, and there's a difference between hitting the cell at its natural resonant frequency and hitting it with a repetitive frequency. And that difference is a little bit like saying I'm going to throw snowballs at the moon, rather than what you actually mean is you're going to throw snowballs in the direction of the moon. Throwing them at the moon, you're never going to get there, you're never going to hit it. And I think that there's a lot of talk from people about hitting the cell at resonance, and quite frankly I don't think they have the understanding to appreciate what that fully means. I may be wrong, of course, but that's just my opinion. Anyway, I hope you found that interesting. Thanks for watching, guys. Bye bye.